and give you an idea of why, one of the reasons that we have the speaker we do today. We are not the same age, but we're not too far apart. But we both grew up shooting Estes rockets off as children. I did it with my children, and these are my grandchildren behind me launching an Estes rocket today, about a month ago. That's my grandson Kai at the launch control. It's my Ava Grace is in the back, is the downrange safety officer, and Tess is part of the recovery team. So my interest in space dates way back, and I'm looking forward to today's speaker. He's Bill Cutlip. He wanted to be an auto mechanic, but he gave that up so he could develop vehicles that go about 150 times the speed of a race car. He spent 37 years with the U.S. government working on everything from mini subs to Navy SEALs to hypersonic vehicle development, to NASA expendable launch vehicle services, and to the OSIRIS-REx program you'll hear about today. He spent 15 years in business development at Goddard Space Flight Center's New Opportunities Office. And his children are there, as they're called, is the instruments on the Curiosity rover on Mars. And they're also on missions orbiting both Mars and the Moon. And of course, the OSIRIS-REx mission that is now orbiting an asteroid hundreds of thousands of miles away. He served as NASA's launch services manager for the Atlas E, Titan II, and Pegasus launch vehicles. And for the work with OSIRIS-REx, he received the NASA Silver Achievement Medal in 2017, and also earned an honor I think we can safely say none of our other speakers will be able to claim. He has a main belt asteroid named after him to recognize his work. Today, he's president of WEC1 Consulting and a senior advisor at Stellar Solutions. He provides NASA academic and the NASA academic and aerospace community with consulting, writing, and editing services for all things mission and instrument proposal related. And he recently served as the primary author of the charter for the University of Arizona's Space Institute. But he's also gotten back to working on his own cars. In his spare time, you can find him driving around parking lots and airport runways and tracks at autocross and track events. And he also plays a lot of tennis, I've found out in the last few days. So, Bill, welcome.
Thank you, Stan. And thank you, and Nancy and Gary, for inviting me to speak today. Appreciate that. And hopefully everyone here will come away from this with a little piece of information I didn't know before, and maybe an even better appreciation of all the neat stuff that NASA does. Little background on myself. As Stan said, I was originally looking to be an auto mechanic, and I'm a product of the Montgomery County, Maryland public school system and the University of Maryland's engineering department and Johns Hopkins master's programs up there. I actually thought I was going to be an auto mechanic, and then heeding the wise words of my mother, she said, "Is that really the best use of your skills?" And I would put it out to everyone listening, listen to your mother. So instead of going off and becoming an auto mechanic, I said, you know what, this engineering thing might have something to it. So that's where I went, and actually spent the first 11 years of my career working for the United States Navy as a mechanical engineer, and then shifted over to NASA and spent almost 29 years there before I retired roughly 2 years ago. It's been a fantastic ride, and I strongly advise it to anyone. And I would be willing to talk to anybody who's on this Zoom. If you have kids in high school that are thinking about what to do in college and everything, drop me a line if you want someone to talk to about what the potential is as far as a career at NASA or the U.S. government in general. I should add that I am a career civil servant, and working for the Navy and NASA is unlike anything you'll ever do anywhere else. I think one of our earlier chats here was someone was mentioning how exciting it is what's going on in rocketry right now, and I couldn't agree more. actually stood in a lunchroom line with Elon Musk several years back, and that was interesting. You're ready to order your salad and fries and a soda, and all of a sudden you notice that Elon Musk is the person in front of you in line. That was rather memorable. So without further ado, let me go ahead and start the presentation. As I understand it, Nancy will be tallying up all the questions as we go. So I will try to keep you fully engaged and enjoying getting up early here. And that's another nice thing I will point out, is that you do get working on it. You get neat. I mean, one of my favorite things is collecting coffee cups from all different missions. And this is one of my favorites. One of our mottos on Osiris Rex was KISS, because we said you would just want to kiss the asteroid. We're not actually landing. We're just going to give it a kiss, take some sample and go back home. So that prompted this coffee cup as far as kissing the asteroid. And we'll talk about that in some slides to come. So let me see if we can go ahead and go to share screen. And I'm going to use that. And we'll go share. There we go. All right. How do I get? Okay, the only question I've got here, Nancy or Gary, is how do I get, or Stan, how do I get the, I'm still seeing the folks, I'm seeing yourself on my screen on top of this. So let me see if I go over here and get rid of that. Well, yeah, we just got to work with that though.
Are you on speaker view, Bill?
Speaker view. Participants polling, new share, pause share, annotate remote control. Pause record.
It's also represented by by 9 dots. 3 rows, 3 columns.
Oh, okay, so hold on, let me get it back up.
We can see it beautifully.
Oh, okay. Well, as long as nobody else can see our faces here, we'll just go with that. All right. Before I get into the nuts and bolts of Osiris Rex, I want to give you a little bit of a science lesson. And I think it's really important because Osiris Rex is definitely a once-in-a-lifetime mission. It falls under NASA's New Frontiers program, which means that they are missions that go out into space. They're planetary missions by definition, and they have budgets, and they actually have, but their budgets are actually capped. They cannot go over, or they get canceled, of $1 billion. So this is as big as NASA gets, with the exception of human flight and what they call flagship missions. So this was actually a competitively won mission. It competed against probably 15 other missions to be selected. So with that, let's talk about science. All right, the first thing is that we do have, for those of you that are maybe a little rusty on where we sit in the universe, there is an asteroid belt in the solar system. As you can see, there we are, the third rock from the sun. And then you have this asteroid belt that exists between Jupiter and Mars. And going even farther out, there's the Kuiper belt. What these two belts contain is some of the oldest matter, really reaching back to the very beginning of our universe. So they're ripe for exploration and seeing what was actually around during that time. The other nice thing, well, I guess you could say nice thing, is that okay, this is where you need to go forward. Why are you not going forward? Oh, modern technology. Okay. Hello. Okay. That's interesting. Why do you not want to go? Ah, there we go. What we end up happening around Earth is we have what are called near Earth asteroids. These are asteroids that have dropped out of the belt and gone into orbits about Earth, Earth crossing. So these are the ones that you'll hear on the news of. It's going to come, so close to the Earth, and don't be afraid. And it's really don't be afraid, folks. NASA's doing a good job of keeping track of all. There's actually a program now to actually keep track of what's going on and how many are out there. So all these blue orbits are all the orbits of near Earth asteroids. So when it came to finding an asteroid to actually study for our science, it came down to, okay, which one are we going to pick? So, oops, well, we're having fun with this here. Let's go. Stan. All right, modern technology. Go away. There we go. So asteroid Bennu is the asteroid that we're actually at right now with the OSIRIS-REx mission. And it took a lot of science to arrive at Bennu. So we actually started out with over 500,000 asteroids that were potential candidates. And then we started narrowing those down. Okay, well, we need to get one that's a near Earth asteroid, because in terms of sampling in our lifetime, we need to go to one of these. Anything that's not a near Earth asteroid, all of a sudden you're talking tens of years, and that's just really too long. So we necked it down to around 7,000 or so. And then we said, okay, as I said, which ones have orbits that we can actually get there, take our sample, get back to Earth in a reasonable amount of time? Well, that took that 7,000 down to 192, not 193, not 195, 192. So then we said, okay, you have to look at ones that are orbiting, have a size such that it makes sense that we can actually do the sampling, because this has to get into the amount of gravity that the mass has, this planetary body has. So we wanted to make sure it had a diameter of greater than 200 meters. And it's probably a good time for you to say, I'm going to keep metric here as much as I can. In some instances, I might stray and go into, heaven forbid, feet and inches and pounds, that kind of stuff. But I'm going to try to stay metric here. So out of the 26, so we've gone from 192 down to 26. And then we said, okay, in terms of our science, we're looking for a carbonaceous chondrite, which means that it is an asteroid that is full of carbon, and obviously carbon being the basis of life on Earth. So that took the 26 down to 5. And then of those 5, we arrived at Bennu. The interesting thing is that the Japanese missions, the Hayabusa mission, Hayabusa 1 and Hayabusa 2, actually went to 2 of the remaining 4 that we did not select. So it really is, there's not a big selection if your science is driving you along with these other criterias. This is interesting. There we go. So this is what you're seeing right now is actual radar data from, because as you can note in the left-hand side, you can see how Bennu passes relatively close, because it is a near-Earth asteroid, passes relatively close to the Earth. And as such, we can get radar imagery. This is one of those sad but true things. The imagery you're seeing right here, the flickering imagery, that was actually taken by the Arecibo radar telescope down in Puerto Rico, which is now no more, because it essentially fell apart. And I've got my fingers crossed that eventually someone will come forth with the money to rebuild that, because that is an incredible asset for the world in terms of science. So you can see that even before we launched, we had a relatively good understanding, we thought, of this asteroid in terms of its size, around 492 meters in diameter. And it is a spinning, what we call spheroidal spinning top sort of thing here. And it had a rotational state 4.3 hours it actually takes for it to do one rotation. So that's good. The other thing to note, and we'll talk about this, I'll talk about this a little bit later, is it is slightly out of plane with the Earth. If you look at the green orbit here that the Earth is on, if you look at Bennu, it's slightly out of plane. And you can also, just for grins, you can see Mercury's orbit. And then the other thing of note is that all of this is happening within Mars's orbit. So that factored into our decision to go with Bennu. It also kind of gives you an idea of when we're sending rovers to Mars, there's a ways to go, and we'll have to wait to see all the neat things that Perseverance does now that it's on the surface. I will note at this time, Stan talked a little bit about the speed. When OSIRIS-REx is orbiting around the sun, it's going, and sorry, I'm going to go non-metric on you. Its average speed around the sun is roughly 63,000 miles per hour. So this is not something you want to get in the way of. Okay, move along. So to give you a little bit more context of the size of Bennu, it's taller than the Empire State Building. It's taller than the Eiffel Tower. It's, I know it's at 492. It's, you know, from our early data, it's closer to 510 meters. So it's larger than the Empire State Building, but it kind of gives you an idea of this is small in the sense of planets, but in terms of planetary bodies, it's still pretty big. We are in scale. You'll show you some other slides here where it's basically the OSIRIS-REx spacecraft looks like basically just a little tiny point, trying to keep things to scale. Our early studies had us convinced that, oh, there's going to be plenty of stuff on what they call regolith on the surface that we can sample. It's great stuff, no problem. So we had done all this study, and as many things in life will do, Bennu threw us a curveball. And I'll talk about that curveball and how we still hit it out of the park, even though it scared the bejesus out of us, because we thought it was going to hit us in the head, as curveballs do. But the team was just fantastic and responded really, really well to it. And you'll see the results on a later slide. What does OSIRIS-REx mean? It's it's a mouthful, and it really gets down to origins, spectral interpretation, resource identification, security, regolith, explorer. So NASA likes their acronyms. This kind of gets everything. Our principal investigator had a bent toward Egyptian history, as far as the gods and everything. So he kind of came up with that. And I actually came up with the Rex part of it because we had submitted this proposal under an earlier NASA opportunity that was about 2/3 of the budget. And luckily we didn't get selected because I think it would have been incredibly hard to pull it off. We went from a discovery class to New Frontiers, which meant you went from around $700 million to $1 billion. So I said, you know what, this has got to be the king of everything. And so why don't we just call it OSIRIS-REx? And then my wonderful scientist just went off and ran with this. And it's like, oh no, Rex actually means regolith explorer. And next thing I knew, it was showing up on decals and coffee mugs and everything else. So there we go. That's my little story there. I'm not going to read all this to you. This is really what the background is of the OSIRIS-REx. And neat thing for any of you that are looking at, a lot of talk about mining asteroids, that is the resource identification part of this mission. We're actually, and you'll see this later in my presentation, we actually were able to see what actually made up this asteroid. And it's a rubble pile, which was kind of interesting. The spectral interpretation has to do with all the great instruments, state-of-the-art instruments we have on the spacecraft. Security, the Yarkovsky effect, It's one of those, if you've got any of the, they always had them at Sharper Image and everything, where it's inside of like a little windmill sort of thing inside of a glass enclosure, and it spins when the sunlight hits it. What you're seeing as the Yarkovsky effect is just the impact of light onto the surface of an object in space will affect the orbit that it's on over long periods of time. So where you can do your math and go, this is where it should be in an orbit, when you actually then measure it, it's not going to be exactly that, because the Yarkovsky effect actually pushes the object around a little bit, because it heats it and photons emit off of it. And that's just sort of like blowing on your hand is roughly the kind of effect that it has. But if you start doing that over long periods of time, it does account for movement. So, and the last one is really the core of the mission. It's bringing back samples from it, which has never been done in the sense of a pristine sample. And that's what we'll talk about. How do you do that? So, all right. So we get compelling science. Hopefully you agree. And then you need, okay, well, how am I going to get it? How am I going to get this science? Well, you need these state-of-the-art instruments. You need a fantastic spacecraft, and you need a launch vehicle that's going to send you on your way to get there. We still do not have warp drive or anything approaching it. We're still very much stuck in the 50s in terms of propulsion. The rocket we used, the Atlas V 411 for OSIRIS-REx, actually uses refined kerosene. And boy, does that stuff stink. Refined kerosene and oxygen that are combined, liquid oxygen are combined as rocket fuel. And that's where we are right now. So we're still having to get a little help from nature, and we'll talk about that help in a second or two. Here we go. We talked about awesome science instruments. This is the actual spacecraft. So you can see how this is what we call the instrument deck on the spacecraft. The SRC is the sample return capsule. So that's what the head, and I don't know whether I can point this around, but where we say tag SAM arm, this is the arm that you'll see later that actually extends out from the spacecraft. And at the end of that arm is the sampling head. And when we first developed it, it's actually, to give credit where credit's due, folks out at Lockheed Martin out in Denver came up with this. And it's actually a reverse vacuum. And if you think about it, space is a vacuum, so you can't use a vacuum in a vacuum. So this actually is a reverse. Anybody that's ever worked on, done woodworking or let their furniture get real dusty and then blown on that to try to get it out of the way, you remember it kind of blows up in your face when you blow down on it. That's kind of the concept. That's really the concept here. We actually inject ultra pure nitrogen within this head, and it makes the regolith pop up, and then it gets trapped inside the head. That's all we thought we were going to do. Again, another curveball that was thrown at us by Bennu, and we'll see how that curveball worked out a little later in my presentation. The instruments that you see, OTES and OVIRS, they're both thermal instruments. They just cover different parts of the infrared band because we want to image. The rest of these, anything with cam in it, are different types of camera. They're all visual light spectrum. So they were used in the evaluation, the assessment, the gaining a greater understanding of Bennu once we got there. OLA is actually a contributed instrument from the Canadian Space Agency. It's actually a laser altimeter, thus the LA. Rexus is a student experiment that we flew actually out of MIT, and it measures X-rays that are emitted. So I think I got everybody here. Yeah, so yeah, SAMCAM is there just, and you'll see some SAMCAM imagery toward the end of the presentation. It's there just to document that the sample head successfully got inside of the SRC and closed up. I don't have a slide on this, but let me tell you, the SRC, imagine a very small, very small Apollo capsule. What you're seeing in white is actually the heat shield part of it. So it's upside down right now. And that's the way it mounts up. When we get back to Earth in September of 2023, there's actually a spin mechanism underneath that spins it up. It's ejected off the spacecraft and comes into Earth. It has its own parachute, all that kind of good stuff. It's actually going to land in Utah, of all places. There's a Utah test range, which is thousands and thousands of acres of nature that there's nobody that it's going to fall on or anything. And it's a great place to bring your little capsules like this in. And if you're worried about that, I'll remind everyone that all of the Russian spacecraft, all the Russian capsules that go up to the International Space Station, when they bring people back down to Earth, they actually land on solid ground because Russia has a lot of that. And it's a lot cheaper than landing things in the ocean like we like to do for our human crewed ships. So let's go on here. All right, this is where I talk to you about how do we actually get there. You can't get there with it just takes too long if you try to get there under your own power. So what we actually did was, if you look to your left here, when we launched, we actually spent the better part of a year just doing one big orbit around the sun. And you can see how the orbits are all working here, where Bennu was way over here. And as we go around, we actually came all the way around the sun, came back to Earth, and used the Earth as a slingshot. We used what's called a gravity assist. That's what the EGA is, Earth Gravity Assist. And the graphic here on the right, a lot of people are like, well, how do we know you're not going to run back into the Earth? It's like, okay, that would be a bad thing. So we're not going to run into the Earth. But this gives you an idea how close we did come to the Earth. We actually flew under the South Pole. And as we slingshotted under, it gave us that extra oomph. And it also, we used it to change the plane of our orbit. So it put us into the same plane that Bennu's in. You saw from the earlier slide that Bennu's orbit is slightly out of plane from the Earth's orbit. So this accomplished two things. It really cut down the amount of fuel that we needed to have in our onboard propulsion, and it put us into plane. So this was no minor feat. This was a lot of work, a lot of really, really smart people, engineers and scientists figuring out the mechanics of this. So it's a nice little thing you can share with people. It's like, oh, this is how close it came. And there, you can go out on the internet. They actually took some really neat imagery with their cameras as we flew under the pole and looked back at Earth. And I'm not sure whether we have any other imagery quite like that. It's one of the things that Osiris is a neat little side benefit of Osiris coming through. Let me go to the next slide. Quickly, this is just showing, this is another area where Osiris has set multiple new world records as far as flying around such a small object. This is just all the steps that go into how do you safely go down and take a sample, because again, we did not land. Okay, this is just matching the speed of rotation of Bennu. So you're going through space, fantastic speed. You've got something spinning under you, and you've got to go down and match up and find exact spot while you're so far away from Earth. And I've got, here we go. Yeah, so we're just going to leave that. So this just gives you an idea of how complex this is. I like to say, and I'm kind of partial, I like to say it makes the landing of the rovers on Mars look like a walk in the park. We took the sample, as it turned out, the area that was safe to go and take a sample was roughly the size of 4 or 5 parking slots. So this because, and you'll see later, there was a lot of terror all around that area. A lot of big stuff. This is another area where Bennu threw us a curve as far as what its surface actually looked like. And ultimately, this is what we wanted to do once we got there. This is just a little simulation. So that's the sampling head coming down. touches what we thought was going to be a really fine grained surface, blows the gas in, and off we go. Well, things don't always work out exactly the way you want them to, but that's what makes engineering and science great. So this is how it goes back into the head. And it actually disconnects at this joint as it stows itself back and closes up. Oops, come on. There we go. So we got all these pieces, and I think without a doubt, you can say that this mission is the ultimate robotic asteroid mission. This gentleman here on the left is our principal investigator, Dr. Dante Loretta at the University of Arizona. And there you can actually see the spacecraft, that big object there, which a lot of people thought that was a sample return capsule. That's actually the high gain antenna that sends and receives the messages from Earth. And that's another area where, let's go back to little notes here. I have a note there. The amount of time it takes, at the speed of light, it's roughly 35 minutes, I think, right now. I'll check my notes here a little later. So another thing to keep in mind is everything that we're talking about here was all done autonomously. This is not as it is with the rovers. You don't have somebody sitting back on Earth with a joystick. It doesn't work that way. You've just got, there's too much lag. In fact, I think if you watch the landing of Perseverance, they found out everything had already happened by the time they actually cheered about it. It was one of those, okay, it's already done. Now we just have to wait for the data to come back so we can actually confirm everything went right. Same thing with OSIRIS-REx. This whole sampling happened autonomously. Once it started going down to the surface, we had already uploaded all the commands and it was working on its own. It was taking measurements and making adjustments on its own as it went down to the surface. This is not a short mission. As you can see, we launched in September of 2016, and you can see the different phases of it. So right now, we're actually sitting here between the sample collection phase and the departure maneuver, and I'll talk about that in a little bit. This is the full-up spacecraft down at the Kennedy Space Center. So you can see its big solar arrays, and up on top the instrument deck, you can see the sample return capsule there in the center. There's actually a propulsion system, a big tank with hydrazine, which is really, really nasty stuff. If anybody asks you, do you want to go see the hydrazine loading area? Say, can I just see a video of it? You don't want to be anywhere near this stuff. It will kill you. So all these guys are in their what we call bunny suits because we had to keep everything super clean because obviously we're going to get samples from a remote body, and we want to make sure that they're not contaminated, that they remain clean, pristine, as we called it. So you didn't want to take anything with you that might contaminate this. And then as our itinerary here on the right, we have a lot of creative people. We wanted to be like a ticket to go. So you can see all the different steps in the process. It was just a beautiful day when we launched in September of 16. This is Launch Complex 41 down at the Cape, and you can see the Atlantic Ocean out there in front of you. If you imagine yourself about 4 miles back from there, that's where I was. Not the greatest view. One of the downsides of actually working a mission is that if you're lucky, you can throw off your headset and run out of the building and see it going up in the sky. People that have just gone down to watch it actually have better views. Those of us actually working the missions, we're on consoles monitoring, in my case, monitoring different things as far as the status of the launch vehicle, making sure everything was good to go. And there it was. It was just a gorgeous day. We launched on our first attempt. We actually have we had a 30-minute daily window that we had to launch within to match up everything as far as the orbital mechanics of things. So we hit it on the first day, and I wasn't sure we were going to be able to because in typical Florida fashion, we had thunderstorms and lightning the week leading up to it. But then I think we had a little potentially divine intervention because the skies cleared, everything moved off, and off we went. Oops. We talk about how close we are. This is the world record. OSIRIS-REx holds the world record for how close it got in terms of an orbit around a planetary body. If you look down at the bottom, we came within 0.68 of a kilometer of the surface of Bennu. And this kind of gives you, how does that compare to other things? So we were actually closer than the mallard duck flies around, Cessna 172. So it gives you a sense of how close we were. And I don't think that record's going to get broken anytime soon. We broke our own world record a couple times while we were at Bennu in terms of getting down and getting the imagery needed to. So that record, I think, is going to stand for quite a while. Now, we talked about curveballs. To the right is what we thought Bennu was going to look like. On the left is what it ended up looking like. And we're like, oh boy, this is not good. Because you can see where we thought we had a lot of fine material that would be easy to sample, it's a lot of rocks. So let's go to the next one here. This is actually an image from multiple polycam images. As you can see rotating around, this was scary once we got there. It was like, oh, okay, we can't grab samples from these big giant boulders. We need stuff that's not a whole lot different than being at the beach. We also found out that Bennu was active. As you can see here in the upper right hand, all those little dots, that's stuff actually coming off the surface of Bennu. And we think that's just because of the thermal. It's basically rocks, regolith on the surface blowing up when it gets real hot, because, and another surprise, is that this is from the thermal part of it, so you can actually see different colors of heat. We found that, and this is just the size of the boulders, so you can see things were getting really scary. What we found was there's actually water on the surface. So again, you may or may not have heard over the years of the phrase "follow the water." That's been mainly around Mars. It's, this is essential to life as we know it, and I emphasize as we know it, that you have water. And well, sure enough, Bennu has water in its surface. So this is just examples of different. The Murchison is a meteorite that landed on Earth. So you can see in terms of the amount of water for it, it's the green curve. And then what we found on Bennu was actually even more. Obviously, Murchison went through our atmosphere, so it got a little bit torched. So this was just, people were just freaking out. Our scientists were just like, oh, this is so cool. So a lot of surprises. So we said, okay, now we really, really need to make sure that our plan, as far as making sure we know this asteroid, Bennu, like the back of our hand, that's where that kicked in. We had already done all this planning because we thought this would probably, they would throw curveballs at us. So we actually set up this, well, it was already set up. We kicked into this mode of flying every which way around you could possibly doing with our different instruments. And if you don't already have a subscription to Science, go to the library and read. There's actually an issue dedicated to this work. And here we are in all of its glory, rotating around. What we actually did was said, okay, where can we sample? So we started looking around different parts of it, and we came up with the 4 different, they're all named after birds. I was kind of partial, being from Maryland, to the osprey. It ended up being the backup site, with nightingale up in the left-hand corner being the primary. And you can see these little rotates. It's still really, really scary. See, those are not trivial boulders that are around there. So in sake of time, we're going to flip through. This is the actual nightingale site. I'm going to fly you down into it real quickly. And this is all the imagery that we were taking with our different cameras were all stitched together to create these little movies. So you can see as we rotate around and go, okay, that looks kind of, you can see between the big giant scary boulders that it looks like there's a spot down there we can actually sample. It turned out to be a very small site. I'm going to take you out of that. Yeah. And here is with a picture. This is that square to the left. That is 3.5 meters, which is a little shy of 12 feet. When you do the conversion, I think it's actually 11 and a half feet. So it's like, okay, that looks like the place. We're gonna look there. Then we kicked in our other instruments, and this is in the thermal area. And you can see that, again, things got still scary, but okay, we're starting to say this is manageable. We can do this. We had to change some of our parameters a little bit, but you can see all the little yellow dots that were in here. These are boulders that are smaller than 2 centimeters. So, okay, we're like, all right, that we can sample that. So this is where, if we hadn't had the instruments we had on the spacecraft, I think it would have been, I don't know, it would have been a lot scarier. So here's a little showing you, remember I told you it's just gonna be a dot. This is the way we flew in. That's obviously Bennu rotating under us, and we had a little checkpoint to see where we were, and then we start our descent, which is very slow. This is speeded up. And then we said, okay, these match points are when we're matching up with the speed of the asteroid. And then we come down, take our sample, and we're out of there. That was the plan, okay? That was the plan. Just a little kiss and off we go. Let's see if I can get this up. Now, this is, remember the simulation that I showed you? This is actual video from the arm when we touched Bennu. Now, we thought we were just going to kiss the surface, take our, blow the nitrogen gas, take our sample, and off we went. Well, it didn't work out exactly that way. It turned out the surface wasn't exactly the way we thought it was going to be. So we ended up going, we had actually gone 4.5 centimeters into the surface before we even blew that gas bottle. So we were already starting to dig in. And when it all said and done, we actually ended up going about 49 centimeters into the surface. So hardly even needed the gas. We basically just jammed that thing full as we went in. So it turned out to be, we hit our thrusters to back away about 6 seconds into it. And it still took another roughly 11 seconds before we actually came back out and were above the surface where we first touched down. So this was, this was another curveball that our folks did a great job with. This is actually another video showing it was so full that stuff was leaking out of it. So we had a whole series of tests to make sure that it was full. Once we saw that we were actually leaking out stuff, we just made the decision, well, forget that. We're just going to put you into the sample return capsule as soon as possible, which is what we did. And here's, remember I said the SamCam? There it is. That is the real thing, folks. This is from right next door to it, the camera right next door. So you're seeing in space, closing that up, and we're now sitting, because things worked out so well, we actually made some more observations because of the fact that we didn't really fully understand what we thought we understood. So there's actually, we're doing some more observations of the actual site we took the sample. So we've got this farewell observation coming up here in early May. Just to give you an idea, we were talking about how far where all this is happening. Yeah, right now we're 306 million kilometers away from Earth. So, just the round trip of the speed of light, you can see the fact of why so much of this has to happen autonomously. You can't just send a message and go, oh, okay, because by the time that it gets there, things have already happened. So this gives you an idea of where we actually are right now. Well, as of St. Patrick's Day, at least. So that's where we are right now. Time to go home. And we're going to have Earth return in September of 2023. I've already reserved my campsite in Utah. To when it comes in, it's going to be just a wonderful day. And with that, I will conclude my presentation, and I hope you all enjoyed it. Stan, I'm looking for you and taking.
I am here. Thank you, Bill. You timed that almost perfectly. Nancy had to drop off, and so and I haven't had the pleasure of seeing the questions people ask. So I'll just think of a couple that I have. So just in summary, what you're saying is you went 1.2 trillion, 1.2 billion miles and landed on something that was 10 feet across, right?
Pretty much, yes. Yes.
Okay,
Yeah,
so where did you get your GPS system? So.
Yeah, no GPS this deep in space. Yeah, but we were very fortunate. I'm going to stop sharing. Here we go. We were very fortunate. Just a lot of brilliant minds. This is far and away the best team I've ever worked with. I've been part of and worked with. The team was just fantastic. And it was, let's put it this way, the team was so well knit together. I actually have pictures of the PI's 2 children right after they were born. That's a relationship you build with, and we still keep in touch, even those of us that have rotated off the mission because we have other things to do. My direct involvement ended a month after launch, because obviously the launch segment part was done. But I still stayed involved in the mission because I think there's only one person within NASA. There's only one person within NASA that's been that's worked Osiris Rex longer than I have, and he is the program scientist. He actually worked on an earlier version before the Goddard Space Flight Center got involved. But he's also a real close friend of mine.
Okay, well, the precision and the size and the distance and the instruments and so forth make me think maybe this is the future of space travel. Is that of space exploration as opposed to manned missions? Or
it is very much if you look at the missions, the Psyche mission is going to go look at actually an iron asteroid, and it'll be launching in a couple years. The sample return missions are all pretty much, I wouldn't say carbon copies of Osiris Rex, but we've proven this works. These are the kind of instruments. So I think in the future, you're going to see variations of what we've done. In fact, Apophis we're looking at potentially using the spacecraft after we've dropped off the sample return capsule. Here we still got a spacecraft with all these working instruments. What else can we use it for? So so there's already talk about what other bodies can we go to and survey and take all these measurements. Obviously, we can't take any more samples because we don't have a sampling head anymore. But there's still a lot of things we can do with it, which is a great part of this, is that I think the people of the world are getting way more than they paid for, because and on top of that, that's another thing of sample return. A lot of people don't realize we've used, I think, less than 10% of all the rocks brought back from the Earth. And it's been, 40, 50 years since we were on the moon, unfortunately. And less than, I think, 10% of all the rocks that were brought back from the moon have actually been used in science experiments. So you've got, anytime you have a sample return type of mission, it pays dividends over decades, because as instrumentation on Earth gets better and better, you need smaller and smaller pieces of sample in order to do your science.
Okay, we're almost at 9. I will give you one more question. We're here in Virginia. We many of us know about the Wallops Island facility near Chincoteague. Do you see that as being a part of the space program in the future?
Oh, absolutely. No, I spent a lot of time over there. And some of my favorite people work over there. It's already part of it from the Antares rockets that are launching the Cygnus resupply vehicle. So I think they've done a tremendous job working with the state of Virginia there in terms of that spaceport. And you got a lot of places in the United States that are a lot of states that are trying to catch up with what that spaceport, the Virginia spaceport, has done there. So absolutely, absolutely.
All right. And by the way, one thing I didn't mention about Bill is he is now living in just outside Richmond in Midlothian, not too far from me, within easy walking distance.
Yeah.
And I'm sure he would be willing to answer a few questions if people have them. If you send them to me, or we will put a. Maybe, could you mind if we put your email
Oh, sure.
on the when we send the thing out about the video? We'll put his email address on it, and you're welcome to ask him.
Yeah, just no emails about car insurance or mortgage refinance. That'll be fine.
Our car warranties.
That's right, car warranties.
Yeah. All right, Bill. Thank you very much.
You're very welcome.
We really appreciate it. It's been a thrill for me to see this after my next closest thing was I went to space camp when I was about 30 years old.
Yep. Yep.
In Birmingham. So anyway, folks, we will be back on April 27th, and we'll be in touch with you soon about who's there. And as I said, I'll tell you about the video of the event. Thank you very much, Entrepreneur. We'll see you soon. Thanks again, Bill.
Take care. Be safe.